So in a earlier video, we talked about cosmic distance scales and how to think about the scope of the universe in space. What I want to do in this video is talk about the same thing in terms of time. What are the relevant time scales for talking about our universe, and how old is our universe and our solar system and the things in the universe? So the modern contemporary model for the history of the universe is called the Big Bang Theory. The Big Bang Theory we should think of as being distinct from the Big Bang event. We use the word Big Bang in two different ways. I'm going to hammer this into you when we talk about the Big Bang Theory and what the evidence for it is. But we use the words the Big Bang to talk about that moment that the universe began expanding. But we also talk about the Big Bang model to refer to this whole picture of the history of the universe, which says that in the past, the universe was smaller and smaller and smaller and smaller. And if you go back 13.5, 13.6 billion years, everything, all the matter and energy in the universe was compacted into this very small, hot, dense initial state. And the universe has been expanding from that small, hot, dense initial state for 13.5, 13.6. Don't take the last digit after the decimal point that seriously. That digit will change over time as our measurements of distances and times in the universe get better and better. So around 13.5 is the number I tend to say, so that in 5 years when that number is 13.7 or 13.4, my video won't sound out of date, as long as I keep saying about. So the Big Bang model is this picture that the universe has been expanding from this hot, dense state for billions of years. 13.5, between 12 and 14 billion years. So the time scale of our universe is a timeline that lasts 13.5 billion years or so. Our own Earth and our own sun and our own solar system have only been around for about the last third of that, the last 4.5 to 5 billion years. So there was a long history of the universe before our own sun and our own planets formed. This is an important thing to remember, that the history of the universe is more than 13 billion years. The history of our own solar system is only about 4.5 to 5 billion years. Galaxies began to form a few million years after the Big Bang event, after the expansion began. The first stars started to form just a few million years after the Big Bang. Those stars and the gas and dust out of which they formed began to collapse into the first galaxies a few billion years after the Big Bang expansion. We'll talk about that early universe, just a few 100,000 to a few million years after the Big Bang, when we talk about the Big Bang model in more detail. That early universe was very different than the universe we see today. There weren't galaxies of stars. There weren't any planets. There weren't any chemical elements in the universe other than hydrogen and helium for the first few million years. So our own timeline, the timeline for our own Earth and our own solar system, is a timeline that begins about 4.5 billion years ago. Our own Earth has been inhabited for most of that time. There is evidence for life on the Earth, some kinds of life on the Earth, simple microbial bacteria, algae, things like that, dating back all the way to about 3.5 billion years in the past, which is just a billion years after the Earth solidified. In fact, there's some less conclusive evidence that dates back even earlier than that, about 3.8 billion years ago. And the Earth had only just solidified and had liquid oceans just a little while before that, just a few, say, 100 million years before that. Maybe even older. It's hard to find evidence of microbial life, right? Microbes are small, they don't leave fossils, so a lot of this evidence is hard to tease out of the geological record, but there's clear evidence 3.5 billion years ago, convincing evidence 3.8 billion years ago. What are we to make of this fact about life on Earth? When we think about life on Earth in the past, we tend to think of things like dinosaurs, right? Dinosaurs did not exist until about 200 million years ago. on this timeline that is the very, very small fraction of this long history of the Earth. The dinosaurs were a relatively recent phenomenon. Even plants that live on land and tiny, tiny animals that live on land have only existed for about the last 500 million years. That's 500 million years. So the kind of complex life you might think about when you think about life a long time ago is all a relatively recent development. Out of that 4 billion years, only 500 million has been life on the surface, on the land, the dry land. Before that, the 3 billion years before that, the only life on Earth was life in the oceans. In fact, until about 1 billion years ago, so for the first 2.5 billion years or so, there was nothing alive on Earth except for bacteria, microbes, and simple multicellular organisms that lived in the water. So that 3 billion year history of life on Earth is mostly a history of simple single-celled or simple multi-celled organisms. The kind of things we think of as plants and animals are a recent development, only the last 500 million years or so. If we take a look at this picture of the history of life on Earth, where it's kind of as soon as the Earth was solid and had oceans, life appears on Earth, but doesn't do a whole lot of anything for 3 billion years. Well, that's not fair. Bacteria diversified and found different ways to develop food. Photosynthesis was invented. Sexual reproduction was invented rather than just mitosis, splitting in half. But we would still regard everything that happened during that first 3 billion years as quote-unquote primitive life. And the Earth stayed in that primitive biosphere for a really long time. If we are, look, this is an astronomy class. One of the things we're interested in an astronomy class is, might we find life other places in the universe? Right now, that question is speculative. We don't have any examples of life anywhere other than the Earth. So how do we answer this question? One takeaway we might, and I stress that this is a generalization made from one data point, which is very, very bad science. It's barely better than speculation. But if we want to speculate based on the one data point of the Earth, we could say this. It looks like the origin of life is fairly easy. As soon as it was possible for something to live on the Earth, things were living on the Earth. Whatever chemical process leads to life did not take 1 billion years or 2 billion years or 3 billion years to happen. It happened bang, almost immediately after a few 100 million years. But complex organisms like us, or like dinosaurs, or like plants, or like birds, or fish, octopus, that took 3 billion years before that happened. So we might guess that if we look out into the universe, we might find lots of inhabited objects, planets, moons. But that complex life might be comparatively rare. It seems like the process that led to life happened quickly, but the process that led to complex life took a really, really long time. Are we sure about this? No. Maybe it just took a long time on Earth. Maybe other places it happens fast. Maybe the fact that life happened immediately on Earth is itself rare and unusual. We will talk about all of these things, including the question of how did life get started on the Earth in the first place, in another lecture. If we want to take a look at this long time period of the history of the universe, we have to wrap our heads around a huge span of time, billions of years. It's hard to do that. So there is a visualization or an analogy that's usually credited to Carl Sagan, an astronomer from the 70s and 80s who made a very popular TV series in the 1980s called Cosmos, which I watched when I was 13 years old. Carl Sagan's visualization is called the cosmic calendar. It says, rather than trying to imagine billions of years, which is hard to wrap our brain around, let's imagine taking the whole history of the universe and compressing it into 1 year, 1 calendar year, from January 1st on one end all the way to December 31st on the other end. Okay, if we do that, since the universe is a little more than 13 billion years old, every month in the cosmic calendar represents 1 billion years. Every week in the cosmic calendar represents about 250 million years. That's about the time since from now to when dinosaurs evolved, started on the Earth. Every day is about 35 million years. That would mean dinosaurs became extinct 2 days ago on the cosmic calendar. So now is, I'm gonna come over here. Now is the end of, down here, December 31st. At midnight is now. Okay, the Big Bang is January 1st, New Year's Day. So if we think about compressing the whole history of the universe into a year, what does that look like? What does that cosmic calendar look like? Big Bang happens on January 1st. All of the matter and energy in the universe is compressed into an object the size of a baseball, an object the size of a penny. Think about it however you want. Go as small as you need to go. If you keep taking the Big Bang Theory back smaller and smaller, we get to smaller and smaller states of matter and energy. We do not know what happened before the Big Bang. We do not know if it even makes sense to talk about before the Big Bang. We do not know what caused the Big Bang, because cause and effect requires a before. We will talk about what the limits of our understanding are of the Big Bang event when we talk about the Big Bang Theory in more detail. The Big Bang happened on January 1st at midnight, and the universe was in a very hot, dense state. The first stars began to form a few million years around that, say a week later in the cosmic calendar, January 8th or so. The first galaxies did not begin to form until early March in the cosmic calendar, a couple of billion years after the Big Bang. So when we look at this picture from the Hubble Space Telescope of these very, very distant galaxies, the most dimmest galaxies in this picture are the farthest away. We are seeing them as they were soon after they formed, back around a time a few billion years after the Big Bang event. Our Milky Way galaxy was not one of the first galaxies to form. Our Milky Way galaxy began to coalesce out of all of this gas and dust that made up the early universe, say around early May, May 1st or 2nd in the cosmic calendar. So we are already almost all the way up to springtime in the cosmic calendar. Much of the history of the universe takes place without not only our star and our planet, but without our Milky Way galaxy. Our sun does not exist until, and I'm squinting here because my actual screen with my keynote presentation on it is far away and I don't have the notes close to me. That is around September. It's around the second week of September, September 9th or 10th in the cosmic calendar. So our solar system doesn't even, if you think about a year, our solar system doesn't even exist until the fall, until September, October, and November. The Earth is still kind of molten and forming. During that time, our Earth isn't solidified and looks like Earth today until late September, after kind of the middle of September. And the origin of life, the simplest organisms that we have discovered trace evidence of on the Earth, come into being around October 1st. These would be things like bacteria, single-celled organisms, blue-green algae, cyanobacteria, things like that. The earliest organisms were organisms like bacteria that have no cell nucleus. Those are called prokaryotes. Eukaryotes with a nucleus evolve around mid-October. And one really important thing to remember about the Earth is when we think about life and what living things need, if I ask you to make a list of what living things need, I bet a bunch of you would put on that list oxygen, because we, as animals that metabolize oxygen, that breathe in oxygen and use that oxygen to fuel our metabolic processes, need oxygen to live. That is not the case for all living organisms. It's not the case for most plants. It's not the case for bacteria, a lot of bacteria. The reason a lot of bacteria can only be spread by direct contact between you and another organism, or exchange of bodily fluids, is because oxygen kills those bacteria. Oxygen is a highly chemically reactive element. For most of the history of our planet Earth, there was not much oxygen at all in the atmosphere. All of the oxygen in our atmosphere today is a byproduct of photosynthesis in plants and on the land, and algae and photosynthesizing bacteria in the water. So the Earth's oxygen atmosphere that we, as breathing animals, consider essential to life, was not even part of the Earth's ecosystem until about 1 billion years ago. For the first 2 to 3 billion years of the Earth's history, there was no oxygen atmosphere. By the way, if we look out into space and discover some planet and some other planetary system that has an oxygen atmosphere, that planet almost certainly has life, at least plant life, at least photosynthesizing life, because oxygen is so chemically reactive that it will not sit around in an atmosphere for very long unless there's some process replenishing it, processes like photosynthesis. Most of the oxygen on the Earth is not in the atmosphere, it's in the rocks. When you go to the beach and walk on the beach, the sand you're walking on is silicon dioxide. That's a silicon atom and 2 oxygen atoms. Water, all the water in the oceans is H2O. All this carbon dioxide in the atmosphere is CO2. Most of the oxygen in the Earth is not free O2 that we can breathe. It is bound up in other chemical compounds, and that's what oxygen does. So if we find a planet with an oxygen atmosphere outside of our solar system, there are none inside our solar system. We know what all the planets inside our solar system are like. But if we found one in another planetary system, that would be smoking gun evidence that there are biological processes on that planet replenishing the oxygen in its atmosphere. Multicellular life doesn't show up until the second week of December. And by multicellular life, I mean simple multicellular life like sponges and jellyfish. The things we think of as, do I have the Cambrian explosion in here? The Cambrian explosion hits about the second week in December. The Cambrian explosion is this period where the diversification of life, of multicellular life, suddenly happens, and there's many, many different sorts of body plans, sea creatures with shells. Think of the trilobites. Do you know what a trilobite is? I'll show you a trilobite fossil from my office in another video if I think about it. Things with shells, things that fossilize easy. So the Cambrian explosion happens about mid-December in the cosmic calendar. Okay, land plants, and then very quickly thereafter, land animals colonize the land. That's around December 20th or so. We're getting close to the last week of December in the cosmic calendar. The thing we think of as ancient life on Earth, the age of the dinosaurs, is really the week between Christmas and New Year's. It's a very recent period in the history of life on Earth. The extinction of the dinosaurs happened about 65 million years ago. I'm not sure I have a slide of that. And that allowed small animals, mammals, and then primates to fill a lot of those ecological niches. We will obviously talk about the extinction of the dinosaurs because you probably know that there's a theory that the extinction of the dinosaurs was caused by an impact of an asteroid or comet, which is relevant to this course. So our earliest ancestors, small primates, show up a couple of days ago in the cosmic calendar. And humans, what we would recognize as sort of anatomically modern humans, on the cosmic calendar evolve around 10:30 p.m. on New Year's Eve in the cosmic calendar. So an hour and a half before midnight. So if you take the whole history of the universe as a year, all of human existence takes place in that time, between when Ryan Seacrest's Rockin' New Year's Eve starts, and you're making your hors d'oeuvres for your New Year's Eve party at 10:30, waiting for the ball to drop. All of human history, or all of human prehistory, can fit into that last hour and a half. All of human history from which we have written records, fits into the last 10 seconds of the cosmic calendar. So the ball drop on New Year's Eve, as you're counting down 10, 9, 8, 7, those 10 seconds of the cosmic year represent all of recorded human history. So human history occupies a tiny, tiny slice of the history of the universe. Does that mental image help you picture how long 13 billion years is? If you take a 10 seconds at the end of the year and that's all of human history, and you compare that to the whole year, I don't know. It's still kind of hard to wrap your head around what 13 billion years is. But at least it, I think, helps you to frame the difference between human history, a few seconds, history of life on Earth, a few weeks. History of life on the land, a few weeks. History of complex life, about a month. The history of life in general, a couple of months. And understand that there are huge expanses of time in the Earth's history where we would have regarded it as nothing particularly interesting happening. Things really kind of sped up after the Cambrian explosion, those last couple of weeks of the cosmic calendar. So that is one way to visualize the history of life on Earth. I will, if I can find it. There's a. I told you already. I stole this from Carl Sagan's Cosmos. I'll just throw up a link to Carl Sagan's version of this if I can find it on YouTube. I'm not sure if it's up there. Also, some of you maybe, if you're not familiar with Carl Sagan, are familiar with Neil deGrasse Tyson, who sort of remade Carl Sagan's Cosmos series about, I don't know how long ago it was now, probably almost 10 years ago now. And if I can find some, I think Neil deGrasse Tyson also did his own version of the cosmic calendar. So if I can find some of those older versions, and I'll post YouTube links to those as well.